Well, welcome back to our class on software engineering, and we're continuing to make some good progress through our material here. And just as a reminder, we've done this first section onto the real comprehensive way of looking at the basics for software engineering. And now we've been going through this area for system dependability and security. This has been an area of special interest for Somerville and looking at various ways that you can make a robust system. And these last two have been getting more into some of the cybersecurity area. And so this last one that we'll talk about, we'll complete that cycle, and we'll go to chapter 14, talking about resilience. So the things that will be covered, we'll talk about cybersecurity, talk about social technical resilience, and then resilient system design. So the one way to consider resilience is resilience of a system is a judgment of how well that system can maintain the continuity of its critical services in the presence of disruptive events such as equipment failure and cyber attacks. And cyber attacks is unfortunately becoming a more pervasive type of thing. And so cyber attacks by malicious outsiders are perhaps the most serious threat faced by network systems, but resilience is also intended to cope with system failures and other disruptive events. So what are some of the essential resilient ideas? The idea is that some of the services offered by a system are critical services whose failure could have serious human, social, or economic effects. The idea that some events are disruptive and can be affect the ability of a system to deliver its critical services. So the idea that that resilience is a judgment, that is that there are no resilient metrics and resilience cannot be measured, that the resilience of a system can only be assessed by experts who can examine the system and its operational processes. So what are some resilience engineering assumptions? Resilience engineering assumes that it is impossible to avoid system failures, and so is concerned with limiting the cost of these failures and recovering from them. Resilience engineering assumes that good reliability engineering practices have been used to minimize the number of technical faults in the system. It therefore places more emphasis on limiting the number of system failures that arises from external events such as operator errors or cyber attacks. So here's a couple resilience activities: recognition, resilience, recovery, and reinstatement. So recognition, you can't fix what you can't recognize. And so the system or the operator should recognize early indications of system failure. In terms of resistance, if the symptoms of a problem or a cyber attack are detected early, then resistance strategies may be used to reduce the probability that the system will fail. Finally, recovery is if a failure does occur, the recovery activities ensure that critical system services are restored quickly so the system users are not badly affected by the failure. Finally, reinstatement is the final activity of all the system services are restored and normal system operations are continued. So let's talk about resistance. Resistance strategies may focus on isolating critical parts of the system so that they are unaffected by problems elsewhere. Resistance includes proactive resistance, where defenses are included in a system to trap problems, and reactive resistance, where actions are taken when a problem is discovered. So here's the different resilience activities. We have the recognition, resistance, recovery, and reinstatement. And so we already talked about these. And so recognition, this will be the normal statement of operation, and resistance is like when you see that there is a critical service that is being attacked. And if it ends up being successful, then you have to go into system repair, and finally reinstatement software and data restoration. And so here you can see that the various things that would have to take place to put you back into this normal operating mode, which is ultimately the goal of what you want to do. Okay, let's start to talk about cybersecurity. Cybercrime is the illegal use of network systems and is one of the most serious problems facing our society, unfortunately. cybersecurity is a broader topic than systems security engineering. Cybersecurity is a social technical issue covering all aspects of ensuring the protection of citizens, businesses, and critical infrastructure from threats that arise from their use on computers and the internet. Cybersecurity is concerned with all of an organization's IT assets, from networks through to application systems. So what are factors that contribute to cybersecurity failure? You can have organizational ignorance, you can have poor design, you can have human carelessness and inappropriate trade-offs. And so these are things that are all manageable. And so definitely some things that should be thought about in design and redesign. What are some cybersecurity threats? There's threats to the confidentiality of assets, threats to the integrity of assets, and the threats to the availability of assets. For confidentiality, data is not damaged, but it is made available to people who should not have access. For integrity, these are threats where the system or data are damaged in some way by the cyber attack. And finally, availability. These are threats aimed to deny use of the assets by authorized users. What are examples of control? You can have authentication, encryption, and firewalls. For authentication, this is where users of a system have to show that they are authorized to access a system. For encryption, this is where data is algorithmically scrambled so that an unauthorized person can't read or access the information. And finally, for firewalls, this is where incoming network packets are examined, then accepted or rejected according to a set of organizational rules. Firewalls can be used to ensure that only traffic from trusted sources is passed from the external internet to the local organizational network. What about redundancy and diversity? Copies of data and software should be maintained on a separate computer system. This supports recovery after a successful cyber attack. You can have multiple stage diverse authentication. And so this can protect against password attacks. And this is an effective countermeasure. Critical servers may be over provisioned, that is, that they are more powerful than is required to handle their expected load. Attacks can be resisted without serious service degradation. So here's a visual of the cyber resilience planning. And so you need to be thinking about what is the asset classification. Highly important assets are ones that you're going to be working on harder. And then you have the threat identification, and that would fold into threat recognition and threat resistance. And both of those would help you to figure out how and what you're going to be doing for an asset recovery. And then finally, asset reinstatement. And all of these flow into the cyber resilience plan that you would develop. So here's some support for that chart. So for asset classification, this is the organization's hardware, software, and human assets are examined and classified depending on how essential they are to normal operations. For threat identification, for each of the assets, you should identify and classify the threat to the asset. For threat recognition, each threat or sometimes asset threat pairs should be identified on how an attack based on that threat might be recognized. And then for threat resistance, for each threat, you should identify possible resistance strategies. For asset recovery, for each critical asset, you want to work out how that asset could be recovered. And finally, asset reinstatement. This is a more general process of asset recovery where you define the procedures to bring the system completely back to normal operation. What about social technical resilience? Resilience engineering is concerned with adverse external events that can lead to system failure. To design a resilient system, you have to think about social technical system designs and not exclusively focus on software. This deals with these events is often easier and more effective in the broader socio-technical system. So thinking in terms of the Metcare example we've worked through, and so cyber attacks may aim to steal data, gain access using a legitimate user's credentials. Technical solutions may be to use more complex authentication procedures. These irritate users and may reduce security as users leave systems unattended without logging out. Better strategy may be to introduce organizational policies and procedures that emphasize the importance of not sharing login credentials and tell users about easy ways to create and maintain strong passwords. So here's an example of a nested technical and socio-technical system approach. And so keep that in mind. And so you can be thinking in terms of a failure hierarchy. Failure in system S1 may be trapped. And so then it's limited to what is happening to that area. If the failure in S1 leads to a failure in ST1, then it is up to managers in the broader organization to deal with that failure if it starts to migrate beyond an initial area. So what are the characteristics of resilient organizations? They respond to threats and vulnerabilities. They monitor organization and the environment. They anticipate future threats and opportunities, and they learn from experience. And all these, there's an overlap between each of these areas. So there are 4 characteristics that reflect resilience in organization: the ability to respond. Organization have to be able to adapt their processes and procedures in response to risk. And they have to have the ability to monitor. Organizations should monitor both their internal operations and their external environment for threats before they arise. For the ability to anticipate, a resilient organization should not simply focus on its current operations, but should anticipate future possible events and changes that may affect the operations and resilience. And finally, you want to have the ability to learn. Organizational resilience can be improved by learning from experience. It is particularly important to learn from the successful responses to adverse events, such as the effective resilience of a cyber attack. So human error is another thing that needs to be dealt with. So people inevitably make mistakes that sometimes lead to serious system failures. There are 2 things to be considered: the person approach and the systems approach. For the person approach, errors are considered to be the responsibility of the engineer, of the individuals, and unsafe acts are a consequence of individual carelessness or reckless behavior. For a system approach, the basic assumption is that people are fallible and will make mistakes. People make mistakes because they are under pressure from high workloads, poor training, or because of inappropriate system design. So what are some of the system approaches that would be relevant here to talk about? So system engineers should assume that human errors will occur. To improve the resilience of a system, designers have to think about the defenses and barriers to human errors that could be part of a system. Can these barriers should be built into the technical component of the system? If not, they should be part of the processes, procedures, and guidelines for using the system. So here's an example of the layers of defense that you could be laying out in terms of how you could be deferring an attack or errors entering and causing some damage into your system. So you should use redundancy and diversity to create a set of defensive layers where each layer uses a different approach to deter attacks or trap technical human failures. And so there can be various types of system examples. You can have like conflict alert systems, formalizing record procedures, and collaborative checking. So here is an example that you want to avoid is say that a human error, you would like it to be caught, but if using this Swiss cheese model, the last thing you want is to have it go through all these layers and then ultimately cause a system failure. So the defensive layers have vulnerabilities. They're like slices of Swiss cheese with holes in them. Vulnerabilities are dynamics. The holes are not always in the same place, and the size of the holes may vary depending on the operating conditions. Systems of failures occur when the holes line up and all the defenses fail. So you want to be thinking about how to increase system resilience. So you want to reduce the probability of the occurrence of an external event that might trigger system failures. This could be helped by increasing the number of defensive layers. The more layers that you have in a system, the less likely to be that the holes will line up. You could design a system so that diverse types of barriers are included. So the holes with will probably be in different places as a result, and you want to minimize the number of latent conditions in the system. And this means reducing the number and sizes of the system, quote, holds. For operational and maintenance processes, all software systems have associated operational processes that reflect the assumptions of the designers about how the system will be used. For example, in an imaging system in a hospital, the operator may have the responsibility of checking the quality of the images immediately after they have been processed. This allows the imaging process to be repeated if there is a problem. So operational processes are processes that are involved in the using of the system for its defined purpose. For new systems, these operational processes have to be defined and documented. Operators may have to be trained and other work processes adapted to make effective use of the new system. And for personal and enterprise IT processes, for personal systems, the designers may describe the expected use of the system, but have no control over how users will actually behave. For enterprise IT systems, however, there may be training for users to teach them how to use the system. And although user behavior cannot be controlled, it is reasonable to expect that they will normally follow the defined process. What about process design? Operational and management processes are an important defense mechanism. In designing a process, you need to find a balance between efficient operation and problem management. Process improvement focuses on identifying and codifying good practice and developing software to support this. If process improvement focuses on efficiency, this can make it more difficult to deal with problems when they arise. So what about efficiency and resilience? And so you can be thinking of efficient process operation. You can consider process optimization and control, information hiding and security, automation to reduce operator workload and hopefully minimizing errors, and then having role specialization. So these are how the kind of operations you want to be dealing with. And then there's various problem management and mitigation as we're describing here on the other side of this chart. So what about coping with failures? What seems to be inefficient practices often arise because people maintain redundant information or share information because they know this makes it easier to deal with problems when things go wrong. When things go wrong, operators and system managers can often recover the situation, although this may sometimes mean that they have to break rules and work around the defined processes. You should therefore design operational processes to be flexible and adaptable. In terms of provision, information provision and management, to make a process more efficient, it may make sense to present operators with the information that they need when they need it. If operators are only presented with information that the process designers thinks they may need to know, they may be unable to detect problems that does not directly affect their immediate tasks. When things go wrong, the system operators do not have a broad picture of what is happening in the system, so it is more difficult for them to formulate strategies for dealing with the problems. In terms of process automation, this can have both positive and negative effects on the systems. If the automated system works properly, it can detect problems and invoke cyber attack resistance if necessary, and start automatic recovery procedures. However, a problem can't be handled by the automated system. There are fewer people available to tackle the problem. The system may have been damaged by the process automation doing the wrong thing. In terms of disadvantages of process automation, automated management system may go wrong and take incorrect actions. As problems develop, the system may take unexpected actions that may make the situation worse and which cannot be understood by the system managers. Problem solving is a collaborative process. If fewer managers are available, it is likely to take longer to work out a strategy to recover from a problem or cyber attack. Okay, what about resilient system design? So there's several things we want to be thinking about in terms of identifying critical services and assets. Critical services and assets are those elements of the system that allow a system to fulfill its primary purpose. This could be critical services in a system that handles ambulance dispatches, for example. designing system components that support problems, recognition, resistance, recovery, and reinstatement. So having the whole the cyber defense being part of this, that you want to have that included. So for this ambulance dispatch system, you can have a watchdog timer may be included to detect if the system is not responding to events. In terms of survivable system analysis, you want to maintain system understanding for an existing or proposed system, review the goals of the system, sometimes called mission objectives, the mission requirements, and the system architecture. For critical service identification, the services that must always be maintained and the components that are required to maintain these services are identified. For attack simulation, you want to have scenarios or use cases for possible attacks that are identified with the system components that would be affected by these attacks. For survivability analysis, you want to have components that are both essential and compromisable by, you want to have components that are both essential and compromisable by an attack are identified, and survivability strategies based on resistance, recognition, and recovery are identified. So here's the chart that may be helpful in terms of the stages of survivability analysis. You want to review the system requirements and architecture, identify critical services and components, and identify the possible attacks and compromisable components, identify soft spots and survivability strategies, and then you flow that back into the requirements. So it's an iterative process to try and make your system more resilient. What about problems for business systems? The fundamental problem with this approach to survivability analysis, its starting point is the requirements and architecture documentation for a system. However, for business systems, it's not explicitly related to a business requirement for resistance. The belief is that these are a more appropriate starting point than technical system requirements. It assumes that there is a detailed requirement statement for a system. In fact, resilience may have to be retrofitted to a system where there is no complete or up-to-date requirements document. So here's a figure for resilience engineering. So you want to identify the business resilience requirements. And so you have reinstatement, the flow for that, recognition and resistance, recovery, and testing. And so these are the different modes, the different tracks that you want to be aware of. So streams of work in resilience engineering. The first one is identify business resilience requirements. You want to plan how to reinstate systems to the normal operating system. You want to identify system failures and cyber attacks that can compromise the system. You want to plan how to recover critical services quickly after damage or a cyber attack, and to be able to test all aspects of resilience planning. In terms of maintaining critical service availability, to maintain availability, you need to know the system services that are most critical, the minimum quality of service that must be maintained, how these services might be compromised, how these services can be protected, and you need to know how to recover quickly if the services become available. For critical assets, you want to be able to identify them during the service analysis and assess maybe hardware, software, data, or people. All of those things would be part of the review. Well, for the Medcare system resilience, it's a system used to support clinicians treating patients. It provides patient information and records to consultants, consultation with doctors and the nurses, and it includes checks that can flag patients who may be dangerous or suicidal. And it's based on a client-server architecture. So that's the general nature of what it is. And we have talked about this already, and this is just a review. So you have the client, various clients plugging into the network, whether it be a doctor or an admin. And so ultimately, they're trying to get authenticated and get access to the patient database. The critical services for the Medcare. So it's an information service that provides information about patients, current diagnosis and treatment. It provides a warning service that patients could pose a danger to them or others, and its availability of the complete patient record is not a critical service, as routine patient information is not normally required during consultation. So those are some perspectives. So the patient record database that maintains all patient information. So these are things that are required. You need to have the database server that provides access to the database. You need to have the network for client server communication. You need to have a local laptop or desktop computers used by clinicians. You need to have a set of rules to identify patients who are potentially dangerous. So those are all needed for regular operation. In terms of adverse events, you could have an unavailability of the database server that would cause issue. You can have a deliberate or accidental corruption of patient records. You could have the infection of client computers with malware, or you can have access to client computers by unauthorized people who gain access to patient records. So here are some recognition and resistance strategies. I won't talk about this in detail, but I'll just refer to the events. You could have a server unavailability, patient database corruption, malware affecting the client computers, or unauthorized access to patient information. And we already had that in a previous chart. And so the first thing you need to do is you need to have a recognition. And so here are the ways how that could happen, and then postulating some resistance strategies over here. And so here is the Medcare system resilience. And so you can have various backup, like you can have a backup server, so you have redundancy in the server network. You could have a database and integrity checker for the database. And you could also have summary of patient records. That is also, you can get some type of integrity check when there is a new transaction going on. You want to have transition logs and database backup. And so this is way how you're maintaining the integrity of the patient database. So how do you go about doing an architecture for resilience? Summary patient records are to be maintained on the local client computer. These computers can communicate directly with each other and exchange information using either the system network or using an ad hoc network. You want to have a backup server to allow for main server failure. So that would be important. You want to have database integrity checking and recovery software. So the integrity checking runs as a background check, checking for signs of database corruption. And if corruption is discovered, it can automatically initiate the recovery of some or all of the data from backups. The transactional logs allow these backups to be updated with details of recent changes. In terms of critical service maintenance, by downloading information to the client at the start of a client session, the consultation continues without server access. The service that provides a warning to staff or patients that there may be a dangerous situation can be implemented using this approach. What about risk to confidentiality? To miss risk to confidentiality that arise from multiple copies of information on laptops. You want to only download the summary records of the patients. So this limits the number of records that can be compromised. You want to encrypt the disk on local computers. Attackers who don't have the encryption key cannot access the disk. You want to do securely delete the downloaded information at the end of the client clinical session. And you want to ensure all network transactions are encrypted. So just to finish up with a couple of key points, resilience is a judgment of how well a system can maintain the continuity of its critical services in the presence of disruptive events. Resistance should be based on the 4R model: recognition, resistance, recovery, and reinstatement. Resilience planning should be based on the assumption of cyber attacks by malicious insiders and outsiders, and that some of these attacks will be successful. Systems should be designed with defense layers of different types. These layers trap human and technical failures and help resist cyber attacks. To allow systems operators and managers to cope with problems, processes should be flexible and adaptable. Process automation can make it more difficult for people to cope with problems. Business resilience requirements should be at the starting point for designing systems for resilience. To achieve system resilience, you have to focus on the recognition and recovery from problems, recovery of critical services and assets, and reinstatements of the system. An important part of design for resilience is identifying critical services. systems should be designed so that these services are protected. In the event of failure, recover as quickly as possible. Okay, well, that's going to end it for our lecture, and that's the last lecture for this part 2 section. Thank you very much.